Okay, let's do BC FRQ number 6 from 2016. Before we even start, we should know that FRQ number 6 is almost always about a Taylor series,
Seriously?
which holds true here. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It's known that f of 1 is 1, f prime of 1 is negative 1 half, and the nth derivative of f at x equals 1 is given by this equation when n is greater than or equal to 2. Alright, part A. Write the first four non-zero terms in the general term of the Taylor series for f about x equals 1. Alright, first let's recall how to write a Taylor series. Remember it's f to the n of x absolute over n factorial times x minus 1, or x minus the center, which in this case is 1. Okay, so the first term, we're looking for f of 1, which we got. That's given. That's 1. And the other things are going to go away because they're to the 0 or 0 factorial, and they're both just 1. Alright, then we need f prime of 1. Great, that's also given to be negative 1 half. Then we'll have our x minus the center, which is 1. Okay, now we need the next term, but we can see that f double prime of 1 is not given. So we're going to have to use that equation and plug in. So, negative 1 squared times 2 minus 1 factorial over 2 squared. Now, so we can see the negative cancels, and this is just 1/4. Great. Plus 1/4. Don't forget that n factorial on the bottom. And then times x minus the center squared. Now we're going to have to do the same thing for the third derivative at 1, because it's also not given. This time we can see the negative is not going to cancel, so it's going to be a negative term. 3 minus 1 factorial on the top. 2 cubed. 2 factorial over 2 cubed is 1/4. And it's going to be negative 1/4. Great. Alright, great. We have our terms. Oop, and don't forget that plus ... Now, don't stop there. We also need the general term, don't forget. For our general term, we can see it's alternating positive, negative. So we need our alternator, and the top's also pretty easy to spot. It just comes from our Taylor series, x minus 1 to the n. Now the bottom's the tricky part here. Rewriting will help us see the pattern. We can see here, it's 2 times that 1 factorial. And here, it's 2 squared times that 2. Then here we got really 2 cubed, because you can take a 2 from the 3 factorial times 3. Now do you see the pattern? We have 2 to the n times n. Great. There's our general term. Now we've answered the whole thing. Now this part A was worth 4 points out of the total 9, which is really great, since the first 3 points are easy to earn. That's just getting the first 2 terms for the first point, then the third term for the second point, and the fourth term for the third point. And those were all quick. Parts of it were given, otherwise we just plugged right into their equation, did simple algebra. Now that fourth term, you need to get the general term, which was easy to either forget or have trouble spotting that denominator pattern. But either way, even if you can't get that, 3 out of 4 is still a solid score here. Alright, let's solve part B now. The Taylor series for f about x equals 1 has a radius of convergence of 2. Find the interval of convergence. Show the work that leads to your answer. Duh. Alright, so we'll call our general term from before a sub n. Looking at this problem, we should know immediately that we need either the root or ratio test. And just like 99% of the cases, it's going to be the ratio test. We can see there's no reason to use the root test here. It's just not set up for it. Alright, we'll plug in to our ratio test equation, a sub n plus 1 over a sub n. Times n plus 1 on the denominator. Now dividing is the same as multiplying by the reciprocal. So we'll do that. Great. Now for the fun part, let's do some canceling. These guys cancel. From that plus 1, we're left with an x minus 1 in the numerator. Same sort of thing with the 2 to the n's. These cancel. Times 1/2 for that plus 1 in the denominator. Now our n terms are going to be n over n plus 1, which just goes to 1. Easy limit, same power in the numerator and the denominators. Great, we've solved our limit. Don't forget your absolute value bars though, and then it's all less than 1 because that was the ratio test. We can see, multiplying both sides by 2, that our interval of convergence is -1 to 3. But we don't know yet if these are hard or soft brackets, if those are included in the interval. But what we do know is that we're probably on the right track because our radius is equal to 2, which they said is true. Alright, real quick, let's test the endpoints. Why don't we plug in 3 first? 3 minus 1 to the n times -1 to the n over 2 to the n times n. Now, these cancel and we see something very familiar, which is the alternating harmonic series, -1 to the n over n, which we know that converges.
Are you serious?
Conditionally, but it doesn't matter here. Converges because alternating harmonic. Let them know why. Alright. Now, let's plug in our other bound, -1. -1 minus 1 to the n over 2 to the n times n. Now, over here, we're going to end up with this. That's times 2 to the n. Cram it in there. This comes from the two negatives, so it's always going to be positive because that to the 2 to the n. Our 2 to the n's cancel, and we are left with another very familiar series, 1 over n. What do we know about 1 over n?
I think it diverges.
Yup, it diverges. Diverges because harmonic. Sweet, we've solved it. -1 to 3, hard bracket, included, and soft bracket, not included. Great, this problem was worth 2 points. The first was just for getting to here, and the second was solving the endpoints, all of which was pretty straightforward, and nice that they give you a little clue like this. Alright, let's solve part C now. The Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms to approximate it. Sweet, this is easy. We found those in part A. All we gotta do now is plug in 1.2. I'll plug in 6/5 because I find fractions a little bit easier to deal with. And for this problem, remember, we don't have a calculator. Now for time's sake, I'm going to let you have the fun of solving this on your own, but you should get 181 over 200, which decimally, if you solve it that way, is about 0.905.
I don't know what you were talking about. That was not fun.
Great. And for this problem, there's only 1 point to earn, and it's for doing what we did and getting this answer. Alright, part D. Show that the approximation found in part C is within 0.001 of the exact value of f of 1.2. Well, reading this, we might first think that we need a Lagrange error bound, but there's an easier way. Remember, we're using an alternating convergent series, so we can just use the error for alternating series. Error for alternating series. Okay, what does that mean? The difference between our actual value of 1.2 and using the third term approximation, which we know had a degree of 2, is just equal to the term that we left out. which was the fourth term when n equaled 3. I'll use 6/5 here again because we don't have a calculator. That's for the 1.2. Great. Slap some absolute value bars on there. And that simplifies down to 1 over 3,000, which is clearly less than or equal to 1 over 1,000. That's that 0.001. Great. We got our first point here. For a correct error form, we use alternating series test. Or not test, error form. You could have used the Lagrange bound. And our last point was for correctly analyzing it, showing that it is in fact less than 1 over 1,000.
If any of these Taylor things were hard for you, just shake it off. No, just kidding. Check out our resources page. Any of the past BC FRQ number 6s, like from 2017, 18, and 23, are great to practice, along with some other links we have posted.